Greetings everyone. I am Riya Shamanto, a student at the Indian Institute of Technology in Kharagpur, India. I am currently pursuing a PhD under the guidance of Professor Somu K. Ghosh of IIT Kharagpur and Professor Shadul K. Das from Missouri University of Science and Technology, USA. I will present our paper, Volunteer Selection in Collaborative Crowdsourcing with Adaptive Common Working Time Slots. This is the brief outline which I should follow today. Whenever we hear the word crowdsourcing, the first thing that comes to mind is the picture of any generalized crowdsourcing architecture that includes clients who post tasks, and from the large pool of available crowd workers, the most suitable candidate is selected for the task based on specific decision criteria. However, crowdsourcing, be it spatial or non-spatial, has shifted from traditionally provision areas to involving large number of people. In this work, we deal with volunteers, and the challenge is to design a proper task allocation strategy to aid in skill-based volunteering crowdsourcing service. Skill-based volunteering is meant to achieve sustainable social and environmental aims. Volunteers are a better option because they help in gaining finer insights about local happenings and are promising for tasks that are otherwise difficult to reach. It is obvious that recruiting volunteers is more cost-effective. At the same time, there are several challenges. Keeping this in, for example, volunteers shall prefer to work at their comfortable time schedule and also closer to their resident. Keeping this in mind, designing an optimal skill-oriented mapping mechanism between such volunteers and tasks with collaboration becomes a real ballgame together. This forms the basis of our motivation behind this work. Now let us move to a real-life example where there is a complex task of a community welfare awareness program. As it is a complex task, it has three subtasks as shown in the picture. That is T1, T1, T2 and T3. Each of these subtasks has its own skill requirements. Now T1 is located at three different places. That is, it has three replicas that are spatially distributed at three geographical locations. The same goes for the other two. We call T11, T12 and T13 replicas of T1 because requirement-wise they are the same as T1, but the location-wise distinct. Now the question is, how the volunteers are to be selected for the replicas of the task as a whole. Now suppose our first problem is solved. We got one or more volunteers selected for the respective replicas. Then how do the volunteers get the most satisfying working time slot for efficient collaboration? From this, we are in the position to define our problem statement. We have two distinct entity types, task with skill requirements and location, and volunteers with skill, current location, and time slot preferences. And next, we have two specific objectives. The first objective is to assign suitable volunteers to the task based on skill requirements and spatial proximity. We call this problem as volunteer task mapping problem. And the second goal is to find the common working time slots which will be suitable for efficient collaboration. We call this problem as common time finding problem. Next, we also derived a utility function UCT, which considers worker C's max skill set with that of task T and cost Z incurred by him. The primary goal is to maximize the overall utility by encompassing all allocated tasks at any given assignment cycle. Thus, we frame our VTM problem as constant optimization problem. These are the contribution. First, we formulate the problem, VTM problem, and then also prove that it is an NP-hard problem. We design and analyze i-VTM, initial volunteer task mapping algorithm for assigning the right volunteers for the right task based on the spatial requirements and spatial proximity. Next, we also design and analyze adaptive common slot finding algorithm for recommending the right suitable common working time slot to the volunteers for the efficient collaboration. We also evaluate our experiments on real-life data set called UpWork. This is the proposed framework. There are two phases. Each can work either independently or as an integrated module. The first phase does the initial volunteer task mapping. The main input are the skill of the volunteers and requirements of tasks along with their location. The output of this space is an allocation map or simply a map, which is a dictionary. The keys are the tasks and values are the selected volunteers. The input to the second phase is the map and the slots of the selected volunteers. The phase does the adaptive common slot finding and returns the refined map and recommend a slot for every replica. We utilized three main data structure. First is the map already discussed in the previous slides. Next is a skill task mapper, in short GST. GST is necessary for maintaining current knowledge of the status of task skill requirement coverage, and it is dynamically modified after each allocation. If combining all the n tasks, there are total m distinct skills, then the size of GST will be m times n. The entries xy is set to 1 if and only if a skill is required by any task y, else 0. GSM or skill volunteer mapper is a subtype of GST. It matches each volunteer's skills to that requirements of the task. Column number is same as the GST except for the rows. If the considered volunteer has M skills, then GSM of that volunteer has M rows. Let's do a quick walk through the workings of the i-VTM algorithm. Among all the available volunteers, the one with the highest skill set is selected. Here the volunteer C1, here the volunteer is C1. A GSM of C1 is also generated. Then we calculate the column-wise sum of the GSM matrix and choose the column index with the highest value. For example, they are T1 and T3. Thus, at this stage, both task T1 and T3 are recommended for C1. Next, we know that T1 has 3 replicas. So the distance of all these replicas from C1 location is calculated. The same is done for T3, which has only 1 replica. We conclude the replica T12 of T1 is the closest and is thus assigned to C1. After that, the GST is updated. Now we see the time complexity of i-VTM is in the order of 80. The next phase is the a-CSF algorithm. The first step is to process the given time slots and convert them to minute-only format. The lower bound theta is set. Thus, for this example, we make it 0.6. This means a resultant common slot is valid if it satisfies at least 60% of the volunteers. Time slot minute array is created, the length of which is always 1440. It stores the total minute count of a day starting from 12 a.m. to 11:59 p.m. And for this bounded array, we could make the time complexity of a-CSF in linear order. We mark the start and end time boundaries of every slot. Then we use prefix sum, which is applied to compute the count of slots. As we see, as we set the theta as 0.6, the number of volunteers to look for would be from 100% to 60% of the total selected volunteers. And this adds the adaptability features to our algorithm. Finally, the time complexity of a-CSF is in order of A dash, where A dash is the number of volunteers selected in phase 1. Experiments are all performed on real-life dataset, which is UpWork. It is a freelancing and crowdsourcing marketplace. These are the 4 baselines which we use for comparison. Next comes the result. Net utility. i-VTM chooses the most skilled workers from the pool and matches him or her with the nearest task, while OG picks up any random incoming worker and matches him with the task that gives the highest utility. Thus, it is intuitive that the most skilled full worker will naturally leverage the highest utility out of all the potential ones. So, i-VTM has the highest score. After that is OG. On the other hand, in case of TM uniform and GMA, every candidate is allowed to use only one skill. So more workers are recruited per task. This is increasing the cost and affects the utility inversely. For success rate, the same reasons stand behind for i-VTM having the highest success rate. The next matrix is the average waiting time. In i-VTM, concurrent matching of any worker with all the present active tasks are performed each time. So, if a worker is rejected or remain unmatched, then he remains unmatched for the entire assignment cycle. Hence, no repeat matching is needed to be performed for the worker during the remaining cycle. This supports the fact that why any task has the least waiting time in i-VTM with respect to the other bases. Completion time. For only i-VTM, first the parent task skill requirements are matched with the worker, and then the replicas are scanned to find the closest one. No requirement matching other than the distance is evaluated for choosing the ultimate replica. Whereas, for the rest, every replica is assumed to be the standalone task having its own skill requirements and location. So at every decision cycle, a worker is picked and pair-wise matching is tried out with every present task, aka replica. GMA and TM uniform perform poorly here because they allow only one skill to be matched, unlike OG and i-VTM. Hence, the completion rate falls as more workers are needed for the task. It is noted that a-CSF does have a positive impact on increasing the satisfactory gain of the assigned volunteers from the task allocation phase. A common working time slot is recommended to initially selected volunteers of phase 1 for every replica, keeping in mind that the threshold lower bound is maintained. Finally, we come to the conclusion of our work. We propose the two-phase framework, which can either work independently or as an integrated module as a whole. The task allocation strategy is based on skill orientation and proximity. Our i-VTM runs in the order of 80, which is quadratic and obviously better than the baselines which compare. Common slot is adapted in nature and considered selected volunteers' preferences only. a-CSF algorithm runs in the order of A, that is in linear, and we also see that a-CSF module can be plugged to any other algorithm, at least the ones which we consider for the baselines. The future work, we are planning to extend this work to include candidates' latent potential level as one of the decision parameters to ensure candidates' long-term retention in crowdsourcing system through certain heuristic and incentives. We are also planning to include the notion of stability in the matching, obviously for one-to-many matching, and we are up to extending this work to the domain of VGI, having both spatial and temporal factors. With this, we come to the end of our presentation. Thank you.